The grounding electrode conductor, or GEC, is a critical component of an electrical system. According to National Electrical Code, or NEC, Section 250.52. A.1. The grounding electrode conductor for a building or structure must be connected to the rebar and concrete-filled footings and to the metal underground water pipe, if available. The conductor must be insulated, copper or aluminum, and sized in accordance with Table 250.66. NEC Section 250.66 requires a minimum size of number 4 AWG copper or number 2 AWG aluminum for the grounding electrode conductor. An inspector's request for 20 feet of insulated wire in the slab is not supported by the NEC. NEC Section 250.64 requires that the grounding electrode conductor be connected to the rebar by a listed grounding clamp. A direct burial grounding clamp complies with this requirement. This queen, or polyethylene sheeting, is not typically required under footings for grounding purposes. However, it may be used for vapor barrier or waterproofing purposes. The grounding system, including the rebar and grounding electrode conductor, is not intended to directly handle lightning strikes. Lightning protection systems are typically separate systems designed to safely redirect lightning energy away from the structure. The inspector's request for 20 feet of insulated wire in the slab is likely due to a misunderstanding or misinterpretation of the NEC. The requirement to install visqueen under footings may also be unrelated to grounding. To summarize, based on this information, it appears that the electrical work was installed in accordance with the NEC. The inspector's request for 20 feet of insulated wire in the slab was unnecessary and not supported by code. The visqueen under footings may have been installed for other purposes. When installing a grounding electrode system, ensure you adhere to the National Electrical Code, or NEC. The purpose of a grounding electrode system is to provide a low impedance path to earth, helping to stabilize voltage to ground during normal operation and limit the voltage rise created by ground faults. The grounding electrode system is not designed to handle direct lightning strikes. That is the purpose of a dedicated lightning protection system. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically at the service equipment. Proper sizing of the grounding electrode conductor is crucial for effective grounding. The size is determined by the size of the service entrance conductors, as outlined in NEC Table 250.66. For example, if your service entrance conductors are 2/0 AWG copper, you would typically need a number 4 AWG copper grounding electrode conductor. Common grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, which are often referred to as UFA grounds, ground rings, and ground rods or pipes. Concrete encased electrodes must be at least 20 feet in length and consist of number 4 AWG or larger bare copper conductor encased in at least 2 inches of concrete. Ground rods must be at least 8 feet long and made of materials like copper, stainless steel, or zinc-coated steel. When driving ground rods, ensure they are driven deep enough to be in contact with the earth along their entire length. If rocky conditions prevent this, the ground rod can be buried horizontally in a trench at least 30 inches deep. When connecting the grounding electrode conductor to a grounding electrode, use listed connectors and clamps suitable for direct burial. These connectors should be made of corrosion-resistant materials to ensure a reliable connection over time. Avoid using dissimilar metals that could lead to galvanic corrosion. The grounding electrode conductor should be continuous, without splices or joints, unless specifically permitted by the NEC. If a splice is necessary, it must be made using irreversible compression connectors listed for the purpose. Protect the grounding electrode conductor from physical damage. If it is exposed to physical damage, it should be installed in rigid metal conduit, intermediate metal conduit, or rigid non-metallic conduit. The conduit must be bonded to the grounding electrode conductor at both ends. The NEC requires the grounding electrode conductor to be securely fastened to the surface on which it is carried. Use appropriate straps, clamps, or other hardware to support the conductor along its length. The path of the grounding electrode conductor should be as direct as possible, avoiding sharp bends or unnecessary loops. This helps to minimize impedance and ensure effective grounding. The grounding electrode conductor should be accessible for inspection and maintenance. Avoid concealing it in locations where it cannot be easily inspected or tested. Regularly inspect the grounding electrode system to ensure that all connections are tight and free from corrosion. Test the resistance of the grounding electrode system to ensure it meets the requirements of the NEC. If the resistance is too high, additional grounding electrodes may be required. In some cases, local codes or regulations may have additional requirements for grounding electrode systems. Be sure to check with your local authority having jurisdiction to ensure compliance. Grounding and bonding are essential for electrical safety. Understanding and implementing proper grounding techniques is crucial for protecting people and property from electrical hazards. Always follow the NEC and other applicable standards when installing and maintaining grounding electrode systems. This detailed explanation should help you to better understand grounding electrode conductor requirements and installation practices according to the National Electrical Code. When dealing with grounding electrode systems, it is important to understand the differences between grounding and bonding, as these terms are often used interchangeably but serve distinct purposes. Grounding refers to connecting the electrical system to the earth, providing a path for fault current to return to the source. This helps to stabilize voltage and limit the voltage rise during fault conditions. Bonding, on the other hand, refers to connecting non-current carrying metal parts together to create a low impedance path for fault current. This ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The main bonding jumper is a critical component of the grounding system. It connects the equipment grounding conductor to the grounded conductor at the service equipment. The size of the main bonding jumper is determined by the size of the service entrance conductors, as outlined in NEC Table 250.28. Equipment grounding conductors provide a path for fault current to return to the source from non-current carrying metal parts such as equipment enclosures, conduit, and junction boxes. These conductors must be sized according to NEC Table 250.122, based on the rating of the overcurrent protective device in the circuit. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electric shock by monitoring the current balance in a circuit. If a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electric shock. Arc fault circuit interrupters, or RFCIs, are devices that protect against electrical fires by detecting arc faults in a circuit. Arc faults can occur when there is a loose connection, damaged insulation, or other condition that causes electricity to jump between conductors. RFCIs are required in many locations such as bedrooms and living rooms, where there is a high risk of electrical fires. Surge protected devices, or SPDs, are devices that protect electrical equipment from voltage surges, such as those caused by lightning strikes or power grid switching. SPD divert excess voltage away from sensitive equipment, preventing damage. SPD are often installed at the service entrance and at individual pieces of equipment. When working with electrical systems, it is important to use proper personal protective equipment, or PPE, to protect yourself from electrical hazards. This includes items such as insulated gloves, safety glasses, and arc-rated clothing. Always follow safe work practices, such as de-energizing circuits before working on them and using lockout/tagout procedures to prevent accidental energization. Regularly inspect electrical equipment and systems to identify and correct any potential hazards. This includes checking for loose connections, damaged insulation, and other signs of wear and tear. Proper maintenance can help to prevent electrical accidents and ensure the safe operation of electrical systems. Electrical safety is a shared responsibility. Everyone who works with or around electrical systems should be trained in electrical safety practices and aware of the potential hazards. By working together, we can create a safer electrical environment for everyone. Always consult the latest edition of the National Electrical Code and other applicable standards when designing, installing, and maintaining electrical systems. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. Staying up to date with the NEC is essential for ensuring compliance and promoting electrical safety. In addition to the NEC, there are other standards and regulations that may apply to electrical systems, such as those issued by the Occupational Safety and Health Administration (OSHA) and local building codes. Be sure to check with your local authority having jurisdiction to determine which standards and regulations apply to your project. Electrical inspections are an important part of the electrical safety process. Electrical inspectors review electrical installations to ensure that they comply with the NEC and other applicable standards. If an installation does not meet the requirements, the inspector will issue a correction notice requiring the deficiencies to be corrected. Working with a qualified and licensed electrical contractor is essential for ensuring the safety and compliance of electrical installations. Licensed contractors have the training, experience, and insurance necessary to perform electrical work safely and correctly. Before hiring an electrical contractor, be sure to check their credentials and references. Understanding the principles of electricity is essential for working safely with electrical systems. Electricity is the flow of electric charge through a conductor. Voltage is the electric potential difference between 2 points. Current is the rate of flow of electric charge. Resistance is the opposition to the flow of electric charge. Ohm's law states that voltage is equal to current times resistance, or volts equals amps times ohms. Understanding Ohm's law is essential for calculating voltage, current, and resistance in electrical circuits. Power is the rate at which electrical energy is transferred. Power is equal to voltage times current, or watts equals volts times amps. Understanding power calculations is essential for determining the size of electrical equipment and conductors. There are 2 types of electrical current: alternating current, or AC, and direct current, or DC. Alternating current is the type of current that is used in most homes and businesses. Direct current is the type of current that is used in batteries and electronic devices. Electrical circuits can be wired in series or parallel. In a series circuit, the components are connected end to end, so the current flows through each component in turn. In a parallel circuit, the components are connected side by side, so the current has multiple paths to flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When the current in a circuit exceeds the rating of the overcurrent protection device, the device will trip, interrupting the flow of electricity. Grounding electrode systems play a vital role in electrical safety. They provide a path for fault current to return to the source, helping to stabilize voltage and limit the voltage rise during fault conditions. Proper installation and maintenance of grounding electrode systems is essential for protecting people and property from electrical hazards. Remember to always prioritize safety when working with electrical systems. Follow safe work practices, use proper personal protective equipment, and consult the NEC and other applicable standards. By working together, we can create a safer electrical environment for everyone.